Today's material is titled Simple Harmonic Motion. This is a type of motion that occurs when objects vibrate around a fixed equilibrium point. It is the most pervasive type of motion in the universe because all atoms and molecules oscillate around equilibrium positions depending upon temperature that will affect our amplitude. So since all materials participate in this type of motion, it is certainly a very pervasive type of motion. We will model this motion by linear restoring force known as Hooke's law. Our two classic examples of this type of motion are a mass attached to a spring. As you can see here, the representation of the mass and the spring, and a simple pendulum. Down here we have a mass attached to the pendulum of a string of length L. We will model these systems, We will model these systems by Hooke's law, which is a simple linear restoring force. The description of the motion, if you look at the words simple harmonic motion, can be broken down as follows. The simple portion is really just simply referring to the fact that the force law is linear, meaning that the force law is proportional to the first power of the displacement, x. Harmonic simply refers to that it is a restoring force. Okay, it could mean we're just going to return the system back to equilibrium. Now that means that the force is opposite. See the negative sign there? The negative sign takes that x and the direction of x and points it in the other direction. So the force is actually in the opposite direction to the displacement x. Notice that the force is proportional to x. This symbol here, K, is our spring constant. It tells us about the elasticity of that spring or the system as a whole. So this is Hooke's law, a linear because it's x to the first power, restoring because the negative sign is in the opposite direction of displacement. This says if you move me to the right, I will exert a force on you to bring myself back to the left, and vice versa. So simple harmonic motion simply refers to linear restoring force acting on the object. As usual, we will start out with our Newton's second law here to try to arrive at an equation of motion of this system. And Newton's second law describes the cause and effect relationship between the force of the spring acting on the mass that is suspended from it. So we're going to use our mass spring system as our template for analyzing simple harmonic motion. So remember that what F says is it's the cause. What is causing M to accelerate? So in our case, we're going to model this by substituting minus kx, which is Hooke's law, for our force acting on M. Take that minus kx over to the right-hand side of this equation. Right? Notice we have a constant m times a plus a constant k times x. So let's just divide the mass m out of the first term and put it under the second term. And then we have a ratio k over m. Well, those are two constants, so rather than carry two constants around, let's simply define k over m as the square of this term here is called omega 0. Omega 0 is defined as the square root of k over m, the natural frequency of this mass spring system. By natural frequency, we're really saying this is the frequency that the system will oscillate with when disturbed. Notice that it depends upon the two attributes of the system, the mass attached to the spring. The spring is characterized by a spring constant K and the mass that is causing the system, that is displacing the system. Okay? So you'll be doing a lab and measuring spring constants to get a feel for that. One thing to say about the spring constant is this, that it is a measure of the spring's resistance to being stretched or compressed. It's the stiffness of the spring. It's the elasticity of the spring. Okay, now, if the natural frequency is given by the square root of k over m, we can also express this in the terms of what's known as linear frequency, or just frequency, f, and the relationship between frequency and omega, the natural frequency, or angular frequency. Remember, we used omega in the previous chapters on rotational motion to describe the angular velocity of an object, which was how many radians did the object rotate per second. Well, we're still using it in the same kind of context, because now we're talking about how many radians per second has this object oscillated through in the process of going up and down on the spring. You may say, well, isn't rotational motion different than vibrational motion? And in fact, we can use the same kind of terms to describe vibrational motion as we used for rotational motion. The idea that there's a frequency, a time, a period, a time it takes to go to repeat this motion in terms of a spring, to go from up to down to back up again, just as there was a repeat time in rotational motion to go around 360 degrees. That means if there's this quantity period which is associated with both types of motion, then remember that the period is 1 over the frequency. Then again, there must be a similar type of term to describe a simple harmonic motion, in other words, frequency. So these two types of motions are really analogous to each other. So we use the term frequency, linear frequency, omega over 2 pi. We use period, 1 over f. And notice that since omega is the square root of k over m, therefore f is the square root of k over m over 2 pi. And if we turn that upside down, we get t, which is 2 pi times the square root of m over k. So that's a theoretical prediction. It says that this is what the equation, when we remember what we applied Newton's second law, using Hooke's law as our model, our mathematical model of how the spring behaves, and we arrived at this natural frequency, and then expressed that natural frequency in terms of the period, and said, this is the time that this system will take to go up and down in its motion. That is the period of motion. So, that's an equation, that's a result from an equation. So, we have to go into the laboratory and then actually apply the spring and mass system and measure the times and see whether or not this is a true expression. In other words, does the theoretical prediction of how much time it takes to oscillate up and down, and notice that it only depends on the mass and the spring, m and k, is that a valid expression for the behavior of a simple harmonically oscillating spring mass system? Now, just as we've done before with kinematics and dynamics of linear motion and rotational motion, our goal really is to be able to describe the motion, position, velocity, and acceleration. Turns out that for simple harmonic motion, we can describe the position x as a function of the time. In other words, this is saying, where are you at any time t? And that is going to be the amplitude, and remember that's the distance from your equilibrium position to your maximum compression or extension. times the sine of omega 0 times t, and plus we've added a phase constant here, phi, to account for a situation whereby the system is, say, pulled down and then released when the clocks start at t equals 0. Otherwise, if you plug in t equals 0 into this equation here, notice that the sine, if t is 0, you'd have the sine of phi, and if we want x to read a, in other words, if we pull the mass down, then we displace it in its maximum amplitude a, and we want x to read a when t equals 0, then we would want the sine of phi to be equal to 1, because x at 0 equals a sine phi. So that would mean phi would have to be pi over 2, or 90 degrees, because the sine of 90 degrees, or pi over 2 radians, is equal to 1. So we incorporate the phase constant in there in order to allow us to use the sine function to describe the motion, whether we start at x equals 0 or whether we start at x equals plus or minus a. For the most part, we won't have to be concerned about that. We'll just use phi equals 0 as our starting point. Going from x, then the position at all times, we can also describe the velocity at all times. Notice that instead of the sine function, now it's the cosine function. And in front of the argument, in front of the cosine function is the product amplitude times omega 0. Notice that has units of velocity, because the amplitude A is in meters and the omega 0 is in radians per second, so per second. Finally, the acceleration, as required, is opposite, negative, a omega squared times the sine again. Notice that the value of the acceleration is a sine function, as is the position. X is also a sine function. Well, let's back up and take a look then at this equation again. Notice right here, okay, this relationship says that m times a and k times x have to sum to 0. Now, the mass can't be negative and k can't be negative, so either a or x has to be negative. If a is negative, then x is positive. If x is negative, then a is positive. So those two have to trade places, one being positive while the other is negative. And then the coefficients in front of a and x have to be equal in order for them to sum to 0. So that's why the sine function, a has a sine function in it, remember, and as x has a sine function, so those two sine functions, both of them will cancel out, and all you're left is with the argument in front of the sine function. For a, you recall it was we still have the mass there, and then a had an amplitude times omega squared, okay, and then k times x, well, the amplitude in front of the sine was a, so that's k times a. So we have ma omega squared, m capital A omega squared, times the sine, and here in k we have k times a times the sine. The sines will cancel, the amplitude will cancel, and you're simply left, after you take everything out, you're actually left with omega squared equals k over m. So it's consistent. In other words, using x equals a sine times the argument omega t plus phi, and using acceleration equal negative a omega squared times the sine omega t plus phi works as solutions to the Newton's second law equation with Hooke's law substituted. So these functions describe the kinematics of a simple harmonically oscillating system. Notice again that the acceleration is not constant, right? Up till now, we've dealt with, in our linear kinematics and our rotational motion, the acceleration was constant. A was, for example, 9.8 meters per second squared, or in rotational motion, alpha was a given number, like 3.5 radians per second squared. So they were constant accelerations. That enabled us to use our kinematics equations in both linear and rotational motion. If you recall, we just simply took the same equations in linear motion and translated them to rotational motion, and we could do that because we were dealing with uniformly accelerated motion, meaning the acceleration was constant. Now you'll notice that because the force is being caused by a spring that obeys Hooke's law, in other words, the force is not constant, but it's changing. It depends on the amount of stretch or compression of the spring. That the force not being constant means that the acceleration is not constant. So we have a changing acceleration, depends on the sine function. We have a changing velocity, depending on the cosine function, and a changing position, all at the same time. Okay? We can use these equations for x and v and so forth in our usual definitions of energy. Remember our energy expression, kinetic energy 1/2 mv squared, potential energy 1/2 kx squared. So if we were to go ahead and plug those definitions of v and x into these equations, you'll notice that you're going to get a cosine squared plus a sine squared. That actually equals 1. And so when we pull everything out side of there and put in a squared omega squared, and down there we have k a squared, and go back to our definitions of that omega is the square root of k over m, the total energy turns out to be a fixed value, a constant. In other words, 1/2 k, which is a constant, and a, which is also a constant. So the total energy of this simple harmonically oscillating system is actually fixed. But notice that the velocity is not constant, nor is the x value constant. But as these two change, as the velocity increases, the kinetic energy increases, the potential energy decreases. Now, where does this occur? Let's imagine visualize this mass going up and down on the spring. The fastest speed occurs when the mass moves through the equilibrium position, the 0 point. Okay? Well, at the equilibrium position, the spring is not stretched or compressed, so it stores no potential energy. So we have 0 potential energy at the point where we have the highest velocity and highest kinetic energy. In contrast that to then at the extreme points where the spring is stretched completely and the object is slowing and then momentarily stopping and then coming back up again, at that point the spring is stretched to its greatest amount, has the greatest amount of potential energy, and of course it momentarily stops, so it has no kinetic energy. So we have a dynamic system here which is trading back and forth between kinetic and potential energy as it moves up and down. But in that trade-off, the total energy stays constant. We can use that as a means of calculating then what is the velocity at the equilibrium point, or what is the maximum extension of this spring in its motion. So notice the maximum, again, this is what I just discussed. The maximum value of x is where it makes an excursion from its equilibrium value here out to plus a or minus a relative to that equilibrium value. Okay? The maximum value of the velocity is when x equals 0, occurs at the 0 point. The maximum value of the acceleration, which is minus a omega 0 squared, the terms in front of the sine function in the acceleration expression, occurs at the two endpoints, the point where the mass turns around in its motion from going up to going down and from going down to going back up. An example of a simple harmonic motion situation might be such as this, where we have a 100-gram mass attached to a spring of spring constant 10 newtons per meter. Notice that 10 newtons per meter is the value of K. Okay? The value of K. K is an expression, once again, of how difficult is it to stretch or compress this spring. And 10 newtons for every 1 meter is what this number is telling us. This mass is seen to oscillate 10 times in 20 seconds, and it goes up and down with an amplitude of 10 centimeters. What is the natural frequency of the system? What is the period? And where is the object located when t equals 1 second? Well, some of the things we know, for instance, we know that K is related to m and omega. Recall omega is the square root of K over m, so that means solving for K. K is m times omega squared. The period is 1 over the frequency, which is 2 pi over the angular frequency omega. So we can solve for omega squared as K over m. Remember that K, which should have been, I guess we would want to make that 100 instead of 10. It seems to have dropped a 0 up there, so newtons per meter, because we're using 100 down here. So K divided by the mass gives us omega, and then we'll take that. Okay. Now the other simple harmonic system that we're using as examples is the simple pendulum. Again, these two systems demonstrate simple harmonic motion most easily and are easily understood. For the simple pendulum, we just simply have a mass attached to a string, a mass m attached to a length of string L. And essentially, we don't bother including the mass of the string. It's negligible compared to the mass on the end of the string. This would be in contrast to, say, a compound pendulum, where the object is oscillating back and forth. It actually has an extended mass to it. Imagine in a grandfather clock, the pendulum and the bob at the end of it may be some elaborate brass structure, and we have to include all of that mass, even the bar that's connecting to the mass at the bottom. And so that would be a compound pendulum, or anything that you might simply grab at one end. To take this pointer here, if this oscillates back and forth, if I could hold on to it, you might say, can I ignore the mass of this barrel here? The answer would be no. It's a significant amount of mass, and so as such I can't just simply say that's not there. With the simple pendulum I would, but with the compound pendulum I have to include that as a part of the system. And the reason for that, it goes back to the idea of moment of inertia, that this object has a moment of inertia, and this is in this axis that is rotating about, which is pointing towards you. This axis defines the moment of inertia relative to that axis, and so we need to take into account all of that object. For a simple pendulum, mass is just simply at the end of a length L, and we would simply have a moment of inertia ml squared. But at any rate, if we went through the same kind of analysis we did for the mass and spring system, and derived the natural frequency and derived the period of the motion, we would find that the natural frequency omega is the square root of g over L, and therefore the period of motion is 2 pi the square root of L over g. And we could measure the angular position by a simple sine function. Measure the angular position by a simple sine function, where theta 0 expresses for us the initial displacement of this pendulum from this vertical line. Here's an example in which we have a brass ball is made to create a simple pendulum with a period of 5.5 seconds. In other words, we want this to oscillate back and forth, one oscillation in 5.5 seconds. And we're going to use that to calculate how long of a cable should we use in order to create this pendulum which will have that period. So given that we know the period, we want it to be 5.5 seconds, let's rearrange this formula to solve for L. Plugging in the period, the acceleration of gravity, and we find that it needs to be 7.51 meters long in order to get a 5.5 second oscillation. So, simple harmonic motion is going to be very useful for us because it will describe for us the velocity of waves, the motion of waves on strings or other media. We'll be able to describe that type of motion using the same type of terminology, such as a wavelength, amplitude, and frequencies. And we will continue to bring that information forward as we go into our next discussion of waves as we continue our simple harmonic motion.